Good morning, everyone. I hope it's a good morning for all of you after the banquet. But today I will talk about shape optimization and deep neural networks, which are some fancy words, but I will tell this presentation as a story. So as every story begins with once upon a time, in my case, once upon a time, there was an ejector. Where you may ask what an ejector is. Well, ejector is a jet pump where at the inlet you have a high pressure liquid which goes through the nozzle, and after the nozzle there's some low pressure, so the ejector can entrain a secondary liquid through the suction. So therefore it's a pump, and from this on the two liquids mix, and at the very end the mixture slows down and the pressure recuperates. And well, why I am talking about ejector? Well, the main reason is that our colleagues, they can do experiments. So, well, every time I come up with some simulation, they can measure it and I can validate the data, which is a really good advantage. And well, we chose to do shape optimization of the ejector. And after discussion with experimentators, they allowed us to change these two parts of the ejector because, well, they are not important for the mixing characteristics and they are also easy to 3D print. And well, what we wanted to optimize, basically, ejector is known for its low energy efficiency, so that's what we wanted to maximize. And we defined it as there's some ratio between the flow rates of the entrained and primary fluid and some pressure recuperation. And we also chose a second objective, which in our case is length. So we want to minimize the length of the device. And well, why we chose the second objective? The reason is that, well, as it is a story, so it has some background. And in the beginning, we did some preliminary work. And when we know that when we make the ejector really big, the energy efficiency is high. And when we make it short, it's low. So when we want to maximize energy efficiency and at the same time minimize the length, we get some trade-off solutions, which, well, usually they are called Pareto optimal front. But we would like to make something more fancy than this. So we, as I said, we change shapes of these two parts. And well, the shape we describe always with length of the part and, well, positions of control points. And for the first converging part, we choose to use 2 control points. If on the diffuser we have 4. So in total, we work with 14 parameters. And well, this is our optimization problem. And as the story continues, we first did the optimization only with CFD, but then we ended up with results we were not really satisfied with. So we tried to speed it up with deep neural networks. But I will start only with the CFD part. So, well, how it works. Basically, this is pretty standard. We use some evolutionary algorithm to govern the optimization, and the algorithm is connected to our CFD model of the ejector, and well, like this we can optimize the problem and get the Pareto optimum front. I should briefly describe how the algorithms works. Basically, if you look at the bottom graph here, every single point is one geometry of the ejector, and the evolutionary algorithms, they work in generations. And basically in the first 1 or 2 generations, all the points are just scattered across the objective space. But as the generations continues, the algorithm uses some random operators based on evolution, and the algorithm can focus more and more on the Pareto optimum front. And you can see that in one run it can find very big chunk of it, which is big advantage of these algorithms. Also, they are robust, but you can see that there are a very lot of points, so it means a lot of evaluations of CFD. But to the CFD, we are on an open forum conference, so I will describe the CFD model a bit more. Here in the middle is the ejector device. The ejector is symmetric, so we could use some 2D axisymmetric approximation to the axisymmetric mesh. And well, since the flow in the ejector is turbulent, we also need to focus on the refinement near the walls. And well, we are very interested in these two parts, in the converging part and in the diffuser. So in there we focused like on the y plus value to keep it below 1, or at least for the default shape of the ejector. And like regarding the equations, we used Reynolds averaging, so these are just standard equations. As a turbulence model, we use the SSTK omega. We chose this model like based on validation with experiments. Regarding the bounding conditions, they're like standard for the velocity and also pretty standard for the pressure. Like the only specialty is this term, which is a resistance term, which we added like based on like experiments, because in the experiment the ejector is connected to some armature and it needs to overcome the pressure when it's entering the secondary fluid. So we added some like experimentally calibrated resistance term. But well, the CFD model works, we validated it, and we used it in the optimization. And here are the first results only with the CFD. Like every cross here is one geometry of the ejector, and in total there were about 9,000 like geometries evaluated, and it took about 1 week on a cluster. And you can see that we found some Pareto optimal front, but in here it's like pretty dense, it's good, but in here it's not so good. Like every engineer would say, okay, and what if I want ejector with this length? How it would look? Yeah, I don't like this shape, so can you give me something more? So that's the problem with engineers, but if you look at the shapes, they can look probably, something like that. You can hear some like edges or some like spikes here. They're like, let's say, I would say interesting. And what we did, like as the story continues, what we did experimental validation. We took these two shapes. We let the experimentators to try to print them and measure it. In the experiment, there was a bit of a problem with experimental conditions because it's hard to keep them constant for different geometries. So we need to recompute our data a bit. These are the recomputed data. But well, the good thing is that the shape that should be better is better, and the shape that should be worse is worse. So this is good. But as I said before, there's a problem with this part of the Pareto front. It is really like sparse. There are big gaps. And if we would like to fill in this part, the CFD optimization would need like weeks and weeks or months to run. So we would like to speed this up with the neural networks. And that's the main reason why we included them. And basically, if I like simply describe the methodology, it's also like standard to like use CFD model to create some samples. And based on these samples, usually people train like some neural network and then substitute the expensive CFD model by the cheap neural network and find the Pareto optimal front more quickly. But there are many, many different types of neural networks, and each type of neural network can like infinite number of architectures. So we had to choose one, and we started with like the simplest thing we could, which is a multi-layer perceptron. It's just a feed-forward network. Well, in our case, in the input layer, we have the parameters. So we have 40 neurons. In the output layer, we have the objectives. So it's two neurons. But in the middle, we have some hidden layers. Yeah. And when we do like very big number of hidden layers, we like we could overfit the problem and did not like play good in the optimization. And also when we have very few hidden layers, it will like make nonsensical results. So there is a problem that we don't know how many layers with how many neurons we want. So what we did to like find the architecture, we implemented or included the neural networks in the optimization framework in a hybrid and adaptive way, let's say. And if I would describe it, we first take the evolutionary algorithm, the CFD model, and we let it run for only one generation. And based on this data, we train a number of, let's say, MPLs with random architectures. Then we took these random architectures, trained, and let them like optimize and get some Pareto optimal candidates. But these candidates, well, we don't know if they are good or not, so we need to somehow like say which is the best candidate. So what we do, we compare like the shape in these with the first generation, and we are looking for similarities. Yes. So, well, the Pareto optimal front with the highest number of similar shapes, let's say, is our best candidate, or I shall say the least wrong candidate. And then we do some like more rigorous testing. So we choose some random shapes from this best candidate and recompute it using the CFD model. And then we like look at the difference between the objective values, and ask ourselves, is it okay? Is the error like small enough? Well, probably no. When we use only one generation, it probably isn't enough. But what we can do is remember the architecture of the MPL that gave us the best candidate. And why is it important? Well, we can use it in the second iteration. So we can let the evolutionary algorithm with CFD run for more generations, and then these random neural networks can be made still random, but similar to the best MPL that we find before. Yes, so they are random, but there's less variation. And well, then it's still the same. We can use it to create some Pareto optimal first candidate, choose the best one or the least wrong, with at least something similar with the two generations we have. Then we can, again, take some samples, recompute them, but, well, usually after two generations it's still not good, but let's say we let it run for enough generations. Still, we have our best MPL, we can create something similar, create the candidates, choose the best, it's all same. But then let's say we run it for enough generations and we are lucky, so the error is small. What we do at the end, we could take like all the data from the last MPL and recompute the with CFD, and we will see what will happen. So that's basically what we did. And if I look at the like adaptive algorithm, how it like converges with the generations, and then you can see that if we gave it only 6 generations like of the CFD optimization, and it was bad. Like the neural networks, even the best neural network wasn't able to like find anything that makes sense. But when we added the generations, and let's say after 18 generations, the neural networks came up with something that looked good. So we said that, okay, 18 is enough. So we rerun this algorithm like 5 times and created a very like big number of samples generated by deep neural networks, and we recomputed them. So if I look at the recomputed data, here is just for you to like remember the old results. This is only CFD. Here is good, here is bad. And what the neural networks find was this. Like in this part, well, it was good, it's good. But the main like good thing is here, because here there were gaps in the CFD, but the neural networks was able to like fill it in a bit and also fill this like little gap. And even the neural network find shapes that, well, like here where no CFD samples were. So we call it a success. We find something new. And if I look at the shapes, like here, just for remembering, here are the old shapes. They look something like this, some staircases, some spikes, some edges. And we were able, using the neural networks, to find some new shapes that, well, some of them look like this. There are some like gaps in the geometry or some very big like edges at the top. So this is the end of the story. And we could ask ourselves if it is a happy end of the story. And well, the answer is we hope it's a happy end. Because, well, we can do shape optimization. We validated the shapes found by CFD by experiment, and we included the neural networks to speed up like the end part of the optimization. And well, in the next steps, we would like to experimentally validate also the shapes that were found by the neural networks. And then we would like to like use this approach to something, let's say, more interesting than an ejector, and maybe in the future include some more like complex architectures of neural networks like convolutional layers and so on. So from me, it's all, and I thank you for your attention.